I'm gonna hand it off to Erin now, who's gonna talk to you about ensembles in R and H2O.
Okay, sounds like this is on. Can you guys hear me? Hi, my name is Erin LeDell. I'm from UC Berkeley. I'm in the division of biostatistics. I'm a PhD student. And my research focus is machine learning and specifically ensemble learning. So I'm here today to talk to you about a software package I've written called H2O Ensemble. And if you can guess by the name, it's an ensemble machine learning method that uses H2O. All right, so my talk today is the overview is, first I'm gonna say what does the term ensemble learning mean? It's kind of a broad term, so we're gonna be a little bit specific about that. Then I'm going to introduce, or just give a quick overview of the H2O R package, because that is what I used to interact with H2O, and I used R to actually write the ensemble code itself. And so that package is called H2O Ensemble, and I'll talk about that. I'll show a couple benchmarks. There's not too many yet. I just finished writing this package a couple weeks ago, so I haven't had a lot of time to play around with it yet. I probably spent more time writing the benchmark code than actually running it. And then I will, if we have time, do a demo on EC2. And just so if you're interested in using H2O on EC2, that will be possibly useful to you as well. Okay, so according to Wikipedia, ensemble methods use multiple models to obtain better predictive performance than could be obtained from any of the constituent models. So in general, the idea is just to take the knowledge from either heterogeneous or homogeneous model sets and combine them in some way to do better than you could with just a single model. So the term ensemble usually refers to, well, it refers to maybe like 8 or 9 different types of things. One of them is something like a random forest, which is an ensemble of weak learners. So the idea there is take a bunch of learners that don't perform well, usually on their own, and because they have high variance, you bag them together, and then the result from that is actually a model that does much better than the individual models themselves. And random forest is very popular because it works well. But that's not what we're going to talk about. What I'm talking about is something that's generally called stacking, and stacking basically takes any kind of model. It could be a random forest, an SVM, a GLM, and just takes these diverse models, and there's sort of a 2-phased training process, which I'll explain a little bit in further detail in a minute. But basically, the idea is diverse models, bringing them together, and you get a stronger model. Okay, so why do people use ensembles? So I've already mentioned that the performance is generally better, but essentially the idea is that you have some set of base learners, and each of them possibly resembles your true prediction function, but maybe not exactly. So maybe your true prediction function is not one of these models that you're considering. So what ensembles do is sort of approximate that true prediction function using all the sort of pieces, building this sort of Frankenstein type of thing. So I've already mentioned this, but ensembles just in general perform better than using a single algorithm. And so I like to think of ensembles as just a little bit more work than what you're already doing when you do a grid search. So if your technique is to train a bunch of models with a bunch of different parameters and sort of, use cross-validation and pick one of them, you've already done, 90-something% of the work of creating an ensemble. So, it depends on your goals. If your goal is to have a simple model, then grid search is probably what you want to do. But if your goal is to have the best performing model, then you might consider an ensemble. And then another reason is if you want to win at Kaggle, you should use ensembles. Okay, so I'm going to talk about what's called the superlearner algorithm, and this is actually just another name for stacking. And I will, in future slides, just do a brief history of where this name came from and what the history of stacking is. But basically, the superlearner algorithm is a loss-based supervised learning method that finds the optimal combination of a collection of prediction algorithms. So the reason that I talk about this algorithm in particular is because there's a bunch of theory behind it. So, and the theory says that it performs asymptotically as well as the best possible weighted combination. So this is basically as good as it gets with your collection. All right, so I'm going to sort of just explain what the algorithm is. So the first step is you define a bunch of models. So let's use the example random forest, SVM, GLM, GBM, whatever you want. And with each of those algorithms, you could have a different set of parameters. So you could have 3 or 4 random forests that have slightly different like M-trie values or something like that. On random forest, maybe that's not super useful, but on something like deep learning where there's a whole bunch of parameters and they give wildly different results, this is something that you could do. So you define your base set. You're going to specify what's called a meta-learning method, and I will also explain in a minute what that means, but essentially just consider it to be another algorithm. And so probably most of you are familiar with what cross-validation is, but that's part of the superlearner is cross-validation. So then, the third step would be just partition your data into V folds. Okay, so think about, I guess, 3 steps of this algorithm. The first step is essentially equivalent to the work involved in doing a grid search with cross-validation. So say you have L algorithms. Basically, you take each of those and do V-fold cross-validation with them to get, say, if you have N training examples, to get N predicted values from that learner. So now, in this phase, you do this L times, and you get these vectors of length N, and sort of stick them together into a new matrix. So then the new matrix we're going to call Z, it has N observations, N rows and L columns. And what that is that becomes your design matrix or your input for your meta learner. So that's how this is also called the level 1 data. And all right, so essentially now we have a new a training problem. So we have Z as our design matrix. We use the same outcome that we used before, Y, and then train this meta learner on that set. So essentially, you think about it as the algorithm takes the input from each of the learners, then recombines it somehow, and then gives you a final prediction. And then, so this is sort of optional. If you are going to save your model, you want to then possibly retrain all the base learners on the full data set. So remember, in step 1, you just did cross-validation. So this is what you would do in a typical situation anyway. You're doing grid search, you find the best model by cross-validation, and then you retrain on the full data so that you have a model that you can use in the future. So just some terminology. So I mentioned already level 0 and level 1 data. Those are the names given to the original training set that you train with the base learners and the cross-validated predicted data set that you train with the meta learner. A learner library, that's just your set of base learning algorithms. The meta learner, as I mentioned, is just the second algorithm that you use. I think I will sort of skip through this section quickly because I don't want to go over. I want to have time for the demo, but I just want to give you sort of a history of where this all this stuff came from. It's been around, I guess, since the 70s. There was something called a model mix, which nobody seemed to know about until at least 1996. So this guy, unfortunately, doesn't really often get the credit that he deserves for sort of inventing this for the first time. The second guy, David Wolpert, is usually the one that is credited with coming up with this idea, and he called it stacked generalization. And he worked at Los Alamos and worked on some sort of speech recognition stuff, and he basically made ensembles with neural nets. And instead of using v-fold cross-validation, he used leave one out cross-validation, which of course takes a lot longer. So then in 1996, Leo Breiman, who's famous for bagging and random forests, wrote a paper called Stacked Regressions. And so he extended the framework to regression problems, and he basically played around with homogeneous base learning sets. So he'd use a bunch of decision trees with different number of terminal nodes and train an ensemble. He'd try subset variable regression with different number of predictors. He didn't really mix and match different types of models that much, although he did mention the idea that somebody could do that. And he came up with sort of the idea of using v-fold cross-validation just because it's a lot faster, and also like some other things having to do with the meta-learner. And there's another paper from 1996 by Michael LeBlanc and Trevor Hasty, and so they kind of took everything that was going on and tried to make it more concise and provide like a general framework for this. And they also played around with bootstrapping for the level 1 data. And then the second to last paper I'll mention is from 1999. Ian Witten is one of the people that wrote Weka. So they basically just extended the framework to work with multi-class. And then in 2007, there's a paper called Superlearner by Mark Vanderland, Eric Pauly, and Alan Hubbard. Those people are at Berkeley. Mark Vanderland is my advisor. And this paper basically provided all the theory behind what these people had been doing. So for a long time, people were intrigued by this idea, but it was a black box. Nobody knew how it worked. And that was okay, because people were getting good results with it. But essentially, there was I wouldn't say no, but like hardly any theory behind what's going on here. And this sort of formalized all of it. And then it sort of took on this new name of Superlearner. So let's see. All right, so just if you haven't used the R interface, this is kind of how it works. You load the H2O library, you make a connection to the H2O cluster. You can import data directly, avoiding R, so you don't have to load it into memory, and that's sort of the key piece here. You can also load it from R, but that's obviously not as good. So the idea is that you have these, there's a handful of functions. One of them, here's an example of the deep learning function. You basically just point to your data, and Y and X in this case are just the names of the columns. And then if you're familiar with R, this looks pretty standard. So then you save a fit and make predictions on a new test set. So it's pretty simple. Okay, so then I use the R interface to make the H2O ensemble package. And let's see, right now it supports binary classification and regression, not multi-class yet. It supports, so there's also an R package called Superlearner, which is written by Eric Pauly, and it's been around since 2009. So what that package does is it has sort of this framework for creating wrapper functions that define certain models. So the SL.star is meant to indicate that you can use those wrapper functions with this package as well. All right, so the ensemble code is on the H2O GitHub at that address. Here's the 4 supervised learning algorithms that you can use in the ensemble. All right, so how do we set up the ensemble? So basically what you see in this learner vector here is just a list of these names, and what these names are names of functions that exist somewhere in your environment. So H2O.glm.1 and .2, those would be like different versions of GLM. Maybe one has one kind of regularization, one has a different kind. So you can make all different versions. And I'll show you on the next slide how to do that. You define your meta learner. NNLS stands for non-negative least squares, and that's a popular meta learner to use. The family argument is that in R, there's usually a family argument in machine learning functions, which indicates what type of prediction you're doing. So binomial would be binary classification. So in the H2O ensemble package, there are these 4 wrapper functions that essentially help you make these functions that define your models. So right now, this is the framework for how models get created, but I'm playing around with like using JSON files and something like a little bit more flexible that doesn't specifically rely on R to define your set of base learners. Okay, so this is how you would train and test the H2O ensemble. It's the X, Y, and data arguments are exactly the same as in H2O. And then there's these 3 extra arguments that you need to define. There's also a couple other arguments, but I didn't list them there. And then the predict is kind of the same as what you would think. Okay, so this is sort of just describes the demo that I'm going to do. I'm just going to go through my slides first and then go over to the demo. So on Amazon, I created an AMI a public AMI that you can use. It's the H2O Ubuntu AMI. And the benchmark, these are the machines that I use, the C3.8 extra large, and those are the specs on those. So, and it uses the Python Boto library to connect to EC2. And the sample data set that I use is this Higgs data set, which I know that Arno has used before with the deep learning examples. So basically, it's a binary classification problem. You're just trying to figure out whether a particular row is background noise or signal. And so these benchmarks are on GitHub, so you can check out the code. And there's instructions how to run this on Amazon, and also you can run it on your laptop if you don't want to use Amazon. So here's just a couple benchmarks. These are pretty tiny benchmarks. I've run it up to like 8 million training points. There's a couple bottlenecks in the code right now that is making it break around that point, but that they're straightforward fixes. I just haven't done it yet. So essentially, it should scale the same way that H2O scales. But right now, there's a couple bugs with the meta learner step that prevents it from doing that. So, but it works up to 8 or 10 million right now. So this particular library, I put 2 random forests, 2 deep learners. I used 5-fold cross-validation to generate the level 1 data. So if you use more folds, that's generally going to lead to better performance, but it takes longer. So you can just choose whatever you have time for. GLM I used as the meta learner. This one was like 160 CPUs, 5 nodes. And so here's just a couple results. So this is test set AUC for these 2 examples. So in both cases, the ensemble does better than any of the individual learners. The bigger data set, it's more pronounced. So remember that the superlearner is asymptotically equivalent to the oracle. So essentially, the more data you have, the better it will approximate that. So it sort of gets better with more data, which is a good problem to have if you have big data. So, and this is sort of just the very first version. There's a lot of improvement that can go into the different meta-learners, and I've done a lot of work on the superlearner package to sort of enable better targeting of particular loss functions that you're interested in with the meta-learning step. And this is pretty much vanilla at this point, so hopefully it'll get better. Okay, so the future work that I'm thinking about doing, and of course I'm open to having help with this, or if anyone, all the code's on GitHub, so it's very easy to collaborate. So one of the things I mentioned was the meta-learners need some work, I think. I would like to have more available. Non-negative least squares would be good. Then I mentioned having user-specified loss functions that you can target. So for instance, I work a lot with binary outcome data where the outcome is very imbalanced. So I care about AUC over other things typically. And so you can write meta-learners that specifically try to maximize AUC. So in the previous results, I was not trying to do that. But there is a project called NLOpt from MIT, and it's just a big library with a bunch of optimization functions that you can access, and basically you just tell it, I want to maximize AUC, and it will give you the, and maybe put some other constraints, like I want the, this is for weighted combinations of the base learners. You say, I want the weights to be positive, or I want them all to sum to 1. You can add constraints depending on which optimization algorithm you're using, and this is something I've done with the superlearner package, and plan to do with this too. The R, yeah, so I mentioned there's some memory bottlenecks I need to take care of. Right now, I'm currently saving the models in just to R, like an R serialized object. So I think I'll probably change that so that you can actually have the H2O versions of the models, and then, say you did all this work, and then after all you decided, oh, actually I just wanted to really pick one model. At least you have that. You've already done the work, so it makes sense to sort of save the models as a group of files, possibly. And so here's just a couple other things. I mentioned the JSON file to define the models. Multi-class would be nice to have. And then ideally, this is sort of like just an experiment to see how this would work. And because the H2O R interface existed, it was easy for me to write it in R. But possibly, the end game would be to implement this in Java and then sort of gut the H2O.ensemble function to just call the Java version of this. But the ensemble itself doesn't do a whole lot of computation. It's just sort of organizing the results from things. So it doesn't really matter that much that it's written in R, but it would, I think, be better if it were in Java. And then also that would enable the other APIs to use it, which is kind of important. So this is my website. I have some other software projects that are, some of them are related to ensembles, some of them are related to other things, if you want to check them out. And now I will attempt to do a live demo of the code. So I'm going to bring up something here. Okay. All right. Okay, so this is, I'll show you here. This is the repo is called H2O Ensemble Benchmark. So what I have running here is the AMI that I put out there, and I think I put the AMI ID, but if you can't find it, you just search for H2O Ubuntu. So when you start up the master node, you're going to want to run this first. That just pulls the most recent version of the benchmarks. So then we'll go into this folder and go to EC2. So the first thing you do is you're going to start a cluster, an Amazon cluster, not an H2O cluster. So these scripts are basically me copying the scripts from the H2O repository on GitHub and then changing them a little bit so that they work with Ubuntu and doing a couple other things. So the names of the scripts are the same as the other ones, if you're familiar. So, so this is going to launch 5 instances, so 5 worker nodes. And let's see, I'll pull up. I was just going to pull up, I guess you can't see this very much, but if you, in Amazon, this is how you search for like an AMI. So if I type in H2O, I'm just doing this while I'm waiting for the cluster to start. So H2O Ubuntu. Okay. So if you type that in, you'll get one result, and that's the AMI that I'm using. So it uses this for the master node and the worker nodes. Okay. So I just have to wait for, I don't know how many of the 60 seconds we've already gone through. But I guess I'll just, actually let me go over here to the code and just go over the steps that I've already done on the master node that you'll have to do. So basically, all you have to do is, there's already a AWS_key.pem file there. It's just a blank file, but you're going to put your private key in there. You want to change the permissions, and then in the bashrc file, you're going to also put your secret key and your AWS keys, and then you're going to source the file. So the scripts that I'm using require these variables to exist. So that's basically all you'll have to do to get this up and running. And actually, the script that I just ran, there's a couple other things you might want to change. Well, you'll definitely want to change the key name to whatever your key is called. And then I have a security group that I call H2O, but it's pretty much just, I think, the default security group. If you have any issues with that, just let me know, and I'll give you more information about that. And then I have the instance type set to this, and then I said 5 instances. So if you want to change any of that stuff, then basically everything past that point will be, you can just use the scripts I have. So let's see. Okay. So the next thing we want to do is distribute the jar file to the nodes. So that's the script that does that. So it's copying over. I don't know why it's, stalled. So we'll wait till that fixes itself. I'm just going to start talking through the demo, and then if it comes back, we'll get there. So the next step would be then to distribute your AWS credentials, and then you're going to start the H2O cluster. And let's see. And then essentially that's all I'm going to show you, because I don't want to make you sit here and wait for all the code to run. So so I'll wait. How about I'll just pause and take questions, and then if the AWS machine decides to behave itself and the jar file gets copied, then we'll just continue. But essentially, I'm just walking you through running a script. So, and all the information about how to do that is so here's the GitHub for this project right here. This README file doesn't have a whole lot of information, but if you go to the EC2, this will walk you through everything that I'm doing or attempting to do. Oh, it's too bad. And then the idea with this repo is that it's sort of just a framework for benchmarking. So I have actually just one training set in there now. You can just add folders of your own training sets and then run the code yourself. So the idea is here, this is a 2-class problem, so I created the 2-class folder, and the Higgs data is there. And so then there's just these 2 files. And this is the one you're going to run. And basically, it just creates a quick R script and like executes and finds out what your cluster IP address is. You're going to change the training set to whatever you want in there. And then this file actually does the benchmarking. So here's where I'm just loading the data from these files. These are a bunch of wrapper functions, or they're functions that create wrapper functions. So I've done that for deep learning and random forest. So this will sort of automatically create a whole bunch of different ones that you can choose from. There's an example how to explicitly create them in the documentation for the package. So if you load the R package and type in like H2O.ensemble, you'll see another example that will show you explicitly how to make those wrapper functions. But you can also look in these files to get an idea. So these are just the names of the functions. Here's my meta learner. Here's me training, predicting, and then I'm calculating the AUC of the predicted, of the ensemble on a test set, and then I'm going through and calculating the AUC on a test set for all the individual base learners to have a comparison. So we'll just check on this real quick. I don't think that's gonna happen, so I will just end and I'll take your questions.
The mic here.
Yeah. Can you score the test data in H2O, or is it going to be in R?
I'm doing it in R, but I think I'm pretty sure that the H2O models they calculate AUC and some other metrics, and so that's actually a better idea than what I'm doing here, which is just you're gonna. At least for the individual models, you can get that information calculated for you. So I'm just doing it explicitly.
Hey, great job. Thank you very much for the presentation. So I was just wondering about the decision-making process you went through in picking H2O to go and do all of this work and sort of investing in their platform. How did you pick going down this route?
Well, I've known about H2O for about, I guess, a year and a half or so. 2 summers ago, I went to a meetup and saw a presentation on H2O's random forest. And then after that, did a whole bunch of benchmarking on the random forest implementation, comparing it to R and the scikit-learn, and then a proprietary implementation as well that's written in C++. And so basically, R and Python kind of didn't, they're just not in the same league as H2O, but H2O was in the same league as the proprietary C++ implementation. So it was sort of, now there's this thing other than scikit-learn and random forest that I can use that's actually fast and it's open source. And so I haven't actively been using it a lot because I have to work on other things in my research, but recently, since they have released the R interface, I've been playing with it more, and so I just decided that I should write it, I guess, yeah. Because I mean, the other implementations of these stacking algorithms are basically in R. There's apparently one in Weka, but I haven't used it. But R just doesn't scale, and so, I mean, I shouldn't say R doesn't scale. R can scale, but not as easily as I wanted it to. So basically, this allows me to have something else, Java, doing the hard work, and then I can just, statisticians can use it because it has an R interface, and that's important to, the people that I work with.
Hey, so I do these from scratch a lot. And I have one quick question and then a different question about your implementation. So I assume you have to line all your crossfolds up with all the algorithms so that they all are doing out of sample at the same time. Is that right?
So actually in other implementations of this algorithm, I've done the parallelism completely differently. So in R, basically all the algorithms are single-threaded. So you can use so there's no way to get more parallelism out of it. So what you do is then parallelize the cross-validation process and all the training stuff. However, with this, it's actually completely different. I originally wrote the code so that it could do that, but the R parallelization sort of conflicts with the H2O parallelization. So it's actually training them in serial, but at each training step, it's maximally using all the cores that you have. So essentially, it's just a different way of parallelizing it, but you're getting the maximum amount of parallelism that you can. And possibly there could be a way to re-architect this software so that you can do, I don't know what the advantages of that would be, but so you could, I don't know, have it even more parallelized, I guess, and get a bigger cluster.
Well, I guess, if you're doing the meta-learning, you're just ensuring that for one record, what you're learning was out of sample for all of the algorithms.
Yeah.
Okay.
Yeah.
The other one is, can you use this if you have multiple targets? Not necessarily a multi-class, although maybe there too, and you said it's not implemented, but if you were to have something where you actually have 3 outcomes and sometimes you can have more than one, I've found that sometimes it's beneficial to have learners learn each of those. So 3 different models that are fit to also each of those 3 targets, send those into a meta-learner. Would that theoretically be possible using this package?
It's not possible right now, but you could make it possible.
Okay. Thanks.
Looks like there's no other questions. Any last minute questions here? Okay, well, thanks a lot, Erin. That was great.